trees have some very specific properties which I like to share with you guys because it helps to, when looking at a graph, to understand what is a tree all about and how can I diagnose whether a graph is a tree or not. Like I mentioned in the last video, this graph was not a tree diagram or a tree graph because there are circuits. It is not minimally connected, which was the fundamental definition of what it means to be a tree. But some of the other properties I think can make it a little bit more quantitative to actually say, okay, how do I know if this graph is a tree or not? The first of which is called the single path property, which states that there is only one path between any of the two vertices on a tree. So like looking back at this graph, say for example between nodes T and V, there's multiple different paths I could take to get from one point to another. That's not something that's happening in a tree diagram. And the idea of a tree diagram or a tree graph is to be minimally connected, basically to have no extra connections, so that when we're actually building the power lines between the two links, we're doing such of a way where we're doing it as minimally as possible. And if you have more than one path, that kind of implies that there's extra connections between the 2 points that were not really necessary. The second property of trees is the all bridges property, that every edge is a bridge on the graph of a tree. And returning to what bridge means was from chapter 5, which we originally defined that. But if you recall, a bridge was an edge that was necessary for the graph to be connected. Or basically, how I phrase it is if that edge were deleted, the graph would become disconnected, right? Kind of as the idea of a bridge is that it's connecting the graph, two different distinct parts of the graph. But when it comes to a tree, every single edge needs to be a bridge because every edge is vital for the connection. Basically, if I was to delete any edge in the graph would fall apart. And the last property is called the n-1 edges property. I think this is the easiest way to determine if a graph is a tree or not, which just states that a tree with n vertices has n-1 edges. And so, like, say for example, that's kind of saying that there's always one less edge than the number of vertices. So say we had 10 vertices, there should be 10 minus 1, or 9 edges in that graph. And all these properties are really the same thing. They're different ways of looking at it. So let's look at a few examples of trees and kind of talk about how these properties apply and help us think about them. But a tree diagram is a fairly standard form of diagram for a lot of different subjects and fields. They're very common in the real world because of what they represent. Like for example, a family tree. Is a very specific type of network that has its own structure. Notice that a friendship graph is not necessarily a tree because, as we talked about, I could be friends with someone through not just one source, but two different sources. And it's actually be very unlikely that a lot of organic networks are trees inherently. But let's look at this very first graph. Basically, let's just use these as examples to look at these properties. But the first property is between any of the vertices, there should be only one path to get from one point to another. And remember, path uses distinct edges. Say, for example, I'm trying to get from point 1 to point 6. There's really only one way to do that, right? There's no alternative path to get there. And that should happen between any of the connections. And one thing I wanted to mention about this is in graph theory, we still typically want to label our vertices with letters, not numbers. So as you can see from these graphs that I chose as examples, they have been numbered, which is actually not good. I'd still advise against you doing this. But it's sometimes it's helpful for the sake of n-1 property. And the n-1 property says that if you have a certain number of vertices, there should be one less edge. So in this case, you have 1, 2, 3, 4, 5, 6 edges. What the n-1 property implies is that that graph should have 5 edges corresponding to 6 vertices. And if we count them up, 1, 2, 3, 4, 5, that's the easiest way to tell if this graph is a tree or not, is just by counting, right? So if we have a number of vertices, we can count by edges. Like looking at the second example, we might not necessarily recognize this to be a tree graph without doing so. But if we were to just count everything, let's count the vertices first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 vertices. That means that this graph should have 17 edges. if it were indeed a tree. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Exactly perfect. Again, very easily we can tell this is a tree. And since this graph appears to have 15 nodes, it should have 14 links. And if it does, it's a tree. Cool. So another property, the all bridges property, and this is basically in line with it needs to be minimally connected. Every edge is vital. Like what you could do in testing that property is think about taking any specific edge and deleting it. Like say in this weird looking insect whatever graph, we were to delete this edge here in the middle. Notice that it would disconnect this region from this region, and we would have two entirely separate parts of the graph. That edge is indeed a bridge by definition. Or looking at this edge, also a bridge, right? Because if that were deleted, it would become disconnected. And this is kind of where the term tree comes from, right? Is in a tree, each of the branches is usually pivotal for holding up part of the tree, right? You take off a branch, the tree falls off. And often the graphs tend to look like branches of a tree, which is where the name comes from. Like, you delete this limb, the whole branch falls off, it becomes disconnected. And it sort of has the resemblance of, limbs. Now, technically with trees, occasionally trees can actually grow back into themselves, but usually trees grow in such a way so that they're trying to get as far away from the ground and from other trees as possible, growing up and to get more sunlight. And usually growing back into itself is not typically very efficient, but and it can actually happen with trees, but typically trees don't do that. Anyways, that's where the idea of tree comes from. And the last term before we move on to some of the ideas behind spanning trees and actually solving those problems is redundancy. Now, in a lot of actual networks, they're not trees inherently, because as we can see from trees, they're a very specific type of graph. And most of the time, when we're dealing with graphs, they're not going to look exactly like this necessarily. Like going back to our initial problem, it was not a tree. So that's one of the issues here. Is our goal is to actually find a minimally connected network because we want to be efficient with our construction of the power lines. And basically the term redundancy is how we refer to how many extra edges that graph has beyond being that of a tree. And I think that's the simplest way to think of this idea. But essentially, if we look at the quantitative definition of redundancy, it says to calculate the redundancy, we can follow this following guideline. And it says to let m be the number of edges in a network and let n be the number of vertices. So this is very common. This is what we did with the n-1 property, which is basically n is going to stand for how many vertices we have. And that was consistent with chapter 5 and 6 as well. And then let's say we're also going to count the number of edges and let that just be m. So it says that if m is equal to n-1, and remember by the n-1 property, this is the condition where if the number of edges is equal to one less than the number of vertices, then the network is a tree. And this is just by the n-1 property for tree graphs. And what we refer to in that case is that graph has a redundancy of 0, meaning that it has no extra edges. That's kind of the idea of what we mean by R as a variable in this chapter. How many extra edges from the minimum does it have? And looking back at these trees, we would say all of these have redundancy 0 because they had no extra edges. But this one definitely has some redundancy because it is not a tree. It has extra connections to it. And then the second, or the last bullet point, I guess, the third bullet point says that if m is greater than n-1, or basically if how many edges we have exceeds how many a minimal graph should have to be a tree, then the redundancy is equal to r equal to m minus parentheses n-1. And really all this is saying is that, well, if our number of edges is more than it should be in a minimally connected graph, it's the difference between how many edges it actually has and how many it should have. And that's going to be the redundancy. So you could use this formula, just figure out what is m, what is n, and plug it in. But I think it's easier just to kind of use common sense to figure out the redundancy. And let's say we wanted to find the redundancy in this graph right here. Basically, you can do it simply by finding the number of edges that we have and how many we should have. So what I first do is count the number of vertices. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's going to be n. I'll go ahead and note that n is equal to 10 here. And since by the properties of trees, by the n minus 1 property, it should have 9 edges. So we could think about that as well. What's n minus 1? That's going to equal 9 in this case. And then what we want to do is figure out, well, what is m? That's how many edges the graph actually has. So the graph has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 actual edges in that graph. And that's going to be what M stands for. And so I can tell that this is definitely not a tree. There are way too many edges. And if we just take the difference between how many it actually has and how many it should has, so basically take M minus n minus 1, the difference between those is 10, and that in this case would be our redundancy. Basically, and what that's saying is there are 10 too many edges in this full graph that we had. And that's how many edges we're going to need to remove in order to figure out an efficient construction. We want to remove, and you can imagine, well, which edges do we not want? We don't want the expensive edges. We want the cheap edges, because the goal is to construct the power lines and save as much money as possible.